Hello everyone. Today let's solve the problem number 1793, maximum score of a good subarray. So what the question states here, we are given an integer array nums. You can clearly see here we are given an integer array nums and index k. This one, this is index, this is nothing but the index k. The score of a subarray I comma j, the score of the subarray, here we have to return the score itself. The score of the subarray I comma j is nothing but the range of the index, that you have to keep in mind, right? I comma j, again I am telling, the score of the subarray I comma j here is nothing but the range from suppose it can, for example, it can be here, we can consider 1 comma 5, means from index 1 to this one 0 index they have mentioned in the question. So this is 0 indexed, so array here this is 0th index, right? 1 comma 5 they have given, means 1, this one from 5 means 1 2 3 4 5, this one, and from starting from 4 to the starting 5, nothing but from the index 1 to index 5. So the score of the subarray I comma j is defined as min of this one. You can clearly see min of nums I comma nums of I plus 1 up to nums of j into j minus I plus 1. So I hope this is clear. What is a good subarray then? A good subarray is one where I is less than or equal to k and k is less than or equal to j. So what we need to find here, we need to find the maximum possible score of any good subarray. So this case what we have to find, we have to find maximum possible score of any good subarray. So that's what we need to find here, right? So here in this case, let's come to the example 1 here. So you can clearly see here we have the nums array and we have the index k equals 3, nothing but third index, right? So how we got here 15, they have clearly explained the optimal subarray is 1 comma 5 here. 1 comma 5 means we are starting from the index 1 for element 4 and we are ending at the index 5, nothing but we have the element 5 here. So here they have given the formula, means first we have to consider minimum within the given range, means 4 3 7 4 5 we have, right? We are considering from here to here. So for out of this one, what is the minimum? Minimum here is 3. So 3 we will consider here for the minimum into this one. So this is nothing but just give me a second here. So within this array, whatever we have considered here, within this array, the last element present at the element present at the last index minus first index plus 1 they have given here. This one I nums of I plus 1 nums of j into j minus I plus 1 they have given here, right? This one we are doing here, nothing but here in this the element present in the last index is 5, right? 5 minus first index we are considering, right? Not the element present at the first index, the index itself we will consider 5 minus 1 plus 1 because they have already given in the question, same thing, right? Plus 1. So this will be 3 into 5 minus 1 plus 1. 5 minus 1 is 4. 4 plus 1 is nothing but 5. This becomes 3 into 5, nothing but 15 in this case. So that's what they have, that's what we have to return in the output. This is the maximum possible score of the given array nums for the index 3 or for the when k is 3, right? So let me delete this one. Let's consider the example 2 as well so that this will be completely clear. So here you can clearly see we have this one. We are going with the optimal subarray 0 comma 4. 0 means we are 0 index, right? 0 1 2 3 4 means until here, from here starting to 4, this one we are considering. So the least number we will consider initially here, the least number will be 4. You can clearly see here 4, and the element present at the last index here as this one we will consider, what we will consider 4. The element present at the last index is 4 and the first index that we are considering here is 0, right? This is 0 index, so this will be 0 here. So what we will do here, 4 minus 0 plus 1, obviously plus 1 they have given in the question, clearly they have mentioned, right? 4 minus 0 plus 1 is nothing but 4 itself, 5 here. 4 into 5 total, this one into this one, 4 into 5 here, nothing but 20. So I hope this is completely clear how we got the output. This is the maximum possible score, right, for the good subarray. So let me delete this one. This is the maximum possible score of a good subarray, 20, and this one 15, how we got. I hope the question is completely clear. What we need to find here, that is completely clear. Let's discuss the approach initially. I'll just consider the same example, this one, example 1. So let's discuss the approach followed by this one, edge cases one by one, and then finally write the code and discuss the complexities of the code that we have written. Initially, let's discuss the approach. So let's discuss the approach step by step here. So first thing we have to keep in mind here is we are going with the data structure. This one, we are going with a sparse table approach, sparse table. Just keep this in mind. We are going with a sparse table. The example, first example that they have given in the question, that itself I have considered here. So it will be easier to understand, right? So we have already discussed. Let's see the approach and let's see how can we articulate that one in the form of code later, right? So again, I'm telling we'll be going with the sparse table, and the first example they have given in the question, that itself I have considered here. Let's move on with the first step. So here, as I have said, we'll be making use of the sparse table by we have to find the minimum value in a given range, right? So within the given range, we have to find the minimum value. Basically, sparse table helps in quickly computing the score for different subarrays. That is the reason we'll be going with the sparse table. So one more thing, you can also go with the two-pointer approach as well. But I wanted to go with the sparse table because it is basically this problem is completely designed to be solved with a sparse table, because we have to find the range minimum queries, right? So in this case, we don't need the this one, what do you call, update function. So suppose we can go for the segment tree as well, but we don't need the update function at all, right? Here only queries we need. Suppose if we are considering, if you want to build the segment trace, usually we go with build this one update as well as the this one prefix sum, or the queries, right? Queries, this one queries update as well as build and initialization. If you are going with the segment trace, we don't need update function at all here. Only this one is required. Queries, computing the queries is required here. So whenever there is a need of computing only the queries, in that case we can make use of the sparse table. It is better than the segment tree, as we go for the big O of one lookup for the query calculation, right? Yeah, for the query calculation it takes only big O of 1. Just keep this in mind. In this case, it is better to go with the sparse table, and you can also go try with two pointers as well, right? So let's go with the sparse table. So first step here is here what we will do, we will construct the sparse table for the range minimum queries. Let's construct the sparse table for range minimum queries. What we will do here, we will pre-compute a sparse table to allow big O of 1 range minimum queries. We have discussed this one. So to compute the we will pre-compute a sparse table. Why we are pre-computing this one sparse table? Basically, it allows big O of 1 range minimum queries, right? That is the reason we'll go with this one. Mainly, that is the only reason we are going with the sparse table as well. So let's move on with the second step. Expand. We will be expanding outwards from index k. When I say expanding outwards from index k, we will start from k equals 3. They have in the question they have clearly mentioned here k equals 3 right here. So they have given the nums array, and they have mentioned in the question that this is 0 indexed. So here k equals 3 means second index we have to consider here. So let me give here index number. So yeah, we have to consider from here, right? K equals 3 they have given. So we will start from k equals 3, nothing but nums of 3. Here in this case, nums of 3, what value we are having here? Nums of 3, nums of 3, when k equals 3, we have to consider this index, right? Not this index, sorry, I said wrong thing. So nums of 3 we have to consider here. In this case, nums of 3 is nothing but here 7. We know this one. Let me come here. Nums of 3 here, the value here, nums of 3 will be 7, right? Nums of 3 means third index. Sorry, I got confused there. So this is fine. Initially left and right we will consider 3, right? Initially left and right we will consider 3, and minimum value is 7. As we are going with nums of 3, the value of nums of 3 is 7. Minimum value we will go with 7. So score will be 7 into this one, 3 minus 3 plus 1. Nothing but here in this case, 3 minus 3 will be 0. 0 plus 1 is 1. 7 into 1 here is nothing but 7 itself. In this case, score will be 7 itself. We will go on expanding left or right, right? Where min of nums of left comma right is maximized. Here, this one they have given in the question. That's what we need to do here. Min of nums of left comma right. L and R is nothing but left comma right here. So we will go on expanding left or right, where min of nums of left comma right within the array is completely maximized. Let's move on with the step 3. Here one step we will expand left, and one step we will expand right. One step again left and again right. That's what we will do here. In this case, we will go with 3 comma 7. So we will consider from 3 here. This one we are considering 3 7 4 5. So let me come here. Yeah, so here first thing we are expanding left to 2, right? Here in this case it will be min of 3 comma 7. Min will be 3 in this case, right? Minimum of 3 comma 7. We are expanding right to 4, means here next value, right? It will be here 3 comma 7 comma 4. Again minimum will be 3 itself, right? So here we were expanding to the left to 1. So minimum will be 4 comma 3 comma 7 comma 4. Again minimum will be 4 in this case. In this case we are expanding right to 5. Min of 4 3 7 4. This one minimum will be 3, right? Here, sorry, I got confused here. Just give me a second here. Yeah, here also min of 4 3 7 4, minimum will be 3. For every this one we have got the minimum value 3 itself, right? Score will be minimum into number of elements that we have considered here, right? So here in this case it will be 3 into 2 elements we have considered, right? Here 3 into 2, here nothing but 6. In this case 3 into 3 it will be minimum into 3 elements is present, minimum into 4, nothing but 3 into 4. Here minimum element, the number of elements is 5. Here minimum element is 3. 3 into 5. In this case it will be 6. In this case 3 into 3 will be 9. In this case 3 into 4 will be 12. In this case 3 into 5 will be 15. And the last one is considered as the output here. So I hope this is clear. We are expanding to find the maximum score. So one step we are expanding to left, next step we are expanding to right, left and again right. Min of 3 comma 7 we considered from the question. You can just check. Next min of 3 comma 7 comma 4, as we are expanding right to 4. Here we are expanding left to 1. 3 7 4 we were already having, 4 we considered in this case, and we are expanding right to 5. Next we had 4 3 7 4. We considered one more element here. So this is 4 3 7 4 5. That's what we did until all the elements are covered for this one. So this is 6 9 12 and 15. The final one will be considered as the answer, nothing but the 15 in this case. So the final output here will be 15, right? This is the answer that we got here. This is that answer or the output that we need to return. So that's what they have shown in the example 1 as well. I hope the approach is completely clear. This is the approach that we will be going with. So in simple terms, we made use of sparse table, right? So I hope this is completely clear. Now let's discuss the edge cases step by step. The first edge case that we'll be going with here is single element, nothing but minimum input size. I can give here minimum input size as well, right? So we'll just go with the one element for the nums array, nums of 5. So k equals 0. So output will be here 0 itself. Why output is 0 here? Output will be 5 here. We have one element. So output will be 5 here. So the only possible subarray is here 5. The only possible subarray is 5, and its score will be quite obviously 5 into 1, nothing but 5. That's what output we got here. I hope this is clear. This is for the first edge case, single element. Second one, when all elements are same. When I say when all elements are same, input we are giving here nums same. Same elements we need to consider here, right? This is fine. K2 we have considered here. Output will be 12 here. Why the output is 12 here? Because the entire array gives the max score. This one. Entire array gives the max score here, right? 3, 3, 3, 3 we will consider. Min equals 3 into elements, the number of elements we have is 4. Min is 3. 3 into 4 is nothing but 12 here. Any element you can consider small because we are having the same elements here. 3 into 4, nothing but 12. Output will be 12 in this case. Let's move on with the case 3 here. K at the start. So here k equals 2 we were having, right, in the previous one. So now we have k equals 0. K at start means k equals 0th index. So output will be 9 here for this. Why the output is 9 here? The best sub array we can go with here is 5, 4, right? So as k equals 0, we have. So 5, 4 score is nothing but here minimum. Minimum is 4, and the number of elements we have here is 2. 4 into 2 here 8, right? So this one will be 8. So output has to be 8, not 9. Sorry, I got confused here. So this is fine. Output will be 8 in this case, right? So just give me a second here. So yeah, output will be 8 in this case. So I hope this is clear. So the edge cases that we considered here as single element, nothing but the minimum input size, and the second one is for the all elements are the same, and the third one is for k at the start. I hope all the edge cases are clear. Now let's start writing the code. So let's start writing the code here. Let me initialize into nums.length here. So we'll be using this one, nums.length. So it's better to go with nums of length. Let's initialize this one to the variable. And first step is we have to pre-compute log values for fast lookup in the this one sparse table. We saw that one during the approach, right? So I can just articulate that one in the form of code in this way. Initially, let's initialize the unsigned 8-bit integer array. So I'll just give here new uint 8 array of n plus 1. This is fine. And let me make use of the for loop. It starts with I equals to I less than or equal to n, and let's increment the I here. So this one will be iterated value of the log will be log of I. So right shift operator, this one plus 1 I'll keep here. So accordingly with the question we are going here, you can make use of any other operator as well. I'll just go with the right shift operator. You can go with the mat.floor as well if it works. So next step, what we have done in the previous step basically, so we were pre-computing the log values for the fast lookup in the sparse table. This was step 1, right? If you remember in the this one approach, this one we consider, I mean this one we have discussed already. So next what we will do, we will go with the maximum exponent value. So I'll just give here max log equals log of n within the array. So we are just going with the maximum exponent value. First thing, next thing, we have to construct the sparse table where sparse of ij stores the minimum range of I, I plus 2 into j minus 1. So that's what they have given in the question as well. So we are constructing the sparse table where sparse of ij stores the minimum range of I, I plus 2 to the power of j minus 1, right? So how can I articulate that one in the form of code here? I'll just consider here sparse equals array dot from I'll make use of initially let's go with the length. I'll go with the length here. Length, let me set this one to the n. So let's go with the length n, array of length n here. This one, new array, let's create. As we can have the negative integers as well, I'll just go with the 32-bit integer array, right? I'll just give here int 32 array of max log plus 1. I hope this is clear, right? So next step is, let's initialize the first column of the sparse table with the array elements. So I'll quickly make use of the for loop here. Let I equals 0, I less than n. So let me give here, let's increment the I. So here it will be sparse of I 0. This one will be iterated value of the nums. So this is fine. So we are initializing the first column of the sparse table with array elements. So the next step here is, let's build the sparse table, nothing but bottom up dynamic programming. We are going with the bottom up dynamic programming. We saw step by step, right? So how can I articulate that one in the form of code? Last step we considered that one 3 into 3, this one 6, 9, 12, 15. Finally we got the output as 15, right? So we have to build the sparse table, nothing but we are going with bottom up dynamic programming. So how can I articulate that one in the form of code? So I'll just give you a simple for loop. J equals 1, j less than or equal to max log. Here let's increment the j. We consider I as well here. Let I of j, we have to I comma j we are considering, right, for the range. So I'll give I comma 0, I, sorry, this will be I plus 1. Let me make use of the left shift operator here. J, this has to be less than or equal to n. Then let's increment the I. So this is fine. So we are just building the sparse table here, right? So mainly within the for loop, sparse of I and j we need to consider. So here this will be math.min of sparse of I and j minus 1. So this is fine. I and j minus 1 we are considering. Again, sparse of I plus here 1. Again, I should have copied this one. This is fine. Let me type this one again. J minus 1. So here I'll come out of this one finally. So we have the array as well right here. Sorry, this one will be j minus 1. This is fine. We have successfully built the sparse table now. Nothing but we went with the bottom up dynamic programming. Let me come out of this one entirely for loop. This one. This is fine. So after building the sparse table, let's make use of the helper function. Nothing but function to query the minimum in the range of left comma r. Suppose in this example we have to go with 1 comma 5, right? So within the range of left comma right. So this is left one, this is right one. You can clearly see here. First index means this is left one, and the last index are right. We are considering last index. This one 1 comma 5 means first index, 0 index, so 1. So fifth index is nothing but the last index. We have the element 4 and 5, right? So here we have to write the function, or we are writing the function to query the minimum in the range of L comma R using the sparse table. Let's quickly write that one. So I'll just come here. Let me write here function query min of left and right. Let me pass this one as parameters here. So initially what I'll do, we have to get the power of 2 for the range. So how can I write here? Let j equals log of r minus L plus 1. Again I'm telling, in this step don't get confused here. We are just getting the power of 2 for the particular range. So that's what we are doing here. After doing this one, let's return math.min of, let me make use of sparse here, left this one will be j. This is fine. So let me give here comma. Again, let me make use of sparse here. This one will be for the right. So I'll just go with right minus 1. Let me make use of the left shift operator here. J plus 1 we have to consider right here. Plus 1 and j will consider here. This is fine. So here what we are doing, we are writing a function to query the minimum in the range L comma R using the sparse table. I hope this is clear. This is just the helper function. Next, let's initialize the max score to 0. We need the max score as the output, right? So max score initially, let's initialize the max score to 0. Also, let's consider left and right. So left and right both will be k, right? So I'll just give here let left equals k. Also, let me initialize right to k as well here. Right to k. So next step, if you remember, we have to expand left and right to maximize the score. So in the third step, we were expanding right, left and right step by step. One step left and one step right. One step left and another step right. So we were expanding left and right to maximize the score. The whatever the maximum score that we got, that we have to return as the output, right? So in this case, I'll just go with simple while loop here. While left is greater than 0 and right is greater than 0, right is greater than n in this case. So this is fine. What we will do, we will get the minimum value in the current range. So when I say min value in the current range, I'll just give here, let's make use of the query min helper function here within this one. Minimum query min of this one, left and right here. So let me make use of left and right. This is fine. The next step, let's calculate the score for current subarray. So max score, we have already considered this one, max score. Initially we have initialized this one to the 0. We have to calculate the maximum score itself, right, for the output. So now let's calculate the score for current subarray. So I'll just give here math.max of, so let me copy this one, same max score min val into right minus left, this one plus 1, let's give here, this is 5. So after doing this, after calculating the score for current subarray, let's check the next possible expansion as well. So next possible expansion, it is available or not. Let's check for that. I'll just give here, let's extend left. So this one we have to go with left right every time. We have to check for left and right. We have to extend left and right if it is possible. So we have to check next possible expansion here. I'll just with extend, sorry, I have already written this one, extend left right. So here I can give, if left is greater than 0, then again let's make use of the query min function here. Query min of left minus 1 comma right. This is fine. Else what we will do, we will return minus 1. So this is fine. This is for extending left. Same thing, let's do it for the right as well. I'll just copy paste and make the necessary changes here. Instead of left, let me consider here right. This one, if right here we have to consider right not greater than 0, less than n minus 1, the last element or the last index, n minus 1. Then this will be query min of, instead of left minus 1, this time we have to consider this one, right plus 1. So I'll just give here right plus 1, left comma right plus 1. If it is not, if we cannot extend right, then we have to return minus 1. This is fine. We are just making use of simple ternary operator. So the final step here is we have to expand in the direction where the minimum remains the largest. So we have to expand in the direction where the minimum remains largest, right? Let's go with a simple if condition here. I'll just give here extend left greater than, if it is greater than extend right here, then what we will do, we will increment the left, else we will increment right. So sorry, we'll decrement left, else we will increment right. This is fine. Final step is we need the maximum score, so we have to return maximum score. So let me copy this one instead, max score here. Let me paste it over here. Let me quickly hit the run button. I hope this works. Let's see. Wrong answer. So let's check what we have done wrong here. So what mistake I have done here is in the line number 5. So in the for loop initial, let's make use of the let here. I forgot to use the let here in the line number 13 as well. So let me give let here, right? So this is fine. Also in the line number 27, so we are going with left greater than or equal to 0. This is fine, and right should be less than n, right? So we are going with the indexing. It shouldn't be greater than n. This miserably fails, so it has to be less than n here in this case. So let me hit the run button now. I hope this works. Let's see. So now you can clearly see. So I had missed let in the for loop, and here in the line number 27, so I had given greater than n here. Right should be always less than n, and left should be always greater than the 0, greater than or equal to 0, right? So this one, these two things I had missed. This is fine. So now the sample test cases are getting passed. Let's see. Let me hit the submit button now. So you can clearly see this one. All the test cases are getting passed here. So the code works absolutely correct in this case, right? So let's quickly discuss the complexities of the code that we have written, right? So the approach that we went with here is sparse table. We know that. So the approach that we went with here is sparse table. And what would be the time complexity here? The overall time complexity would be big O of n log n. Why? Because we are going with the pre-processing, and also it is for the querying it would be big O of n, right? So the overall time complexity would be this one, n plus logarithmic n. It will be big O of n log n, overall time complexity. And what would be the space complexity here? The space complexity would be big O of n log n as well here. So just give me a second here. Let me give here n log n. So why the space complexity here is n log n here? This is, we have to consider the sparse table storage. So the sparse table storage is nothing but it comes with it requires n log n space. So overall space complexity would be big O of n log n here. So the time complexity here would be big O of n log n, and the space complexity would be big O of n log n as well. So overall time complexity would be big O of n log n, and the overall space complexity would be big O of n log n as well. I hope the solution that we have written here is completely clear, right? For now, this is it. Thanks for watching, guys.